Alrighty, so here we are in Circuitverse. Let's just take a peek at some of the D flip-flops and get going on actually building our computer. So if I go down here to sequential elements on the left-hand side of Circuitverse, you can see that we have a bunch of options here available to us. And the one we're going to be using here is this D flip-flop. All right, so yeah, so let's use that, okay? So I'll just drag one of these things in and show you kind of how it works before we get started on actually building the schematic for this computer that we're going to make, okay? So I have my D flip-flop, and as you can see here, we have our two inputs, D and Q, okay? And we also have our clock input, right? And then you can see this implementation of this flip-flop also provides us with a couple of other options for using this flip-flop, right? We have a Q inverse, right? So if Q is a 1, Q inverse is going to be a 0, and vice versa. Sometimes you get that on flip-flops, right? This one has it. And then we also have these reset and enable inputs here on the bottom. Let me just, I'm going to hook up a button for the clock. All right, let's hook up a couple of things here and show you how to use this thing. Okay, I'm going to hook up a button for the clock. I'm going to hook up an input to our input, and then I'm going to hook up an LED for our output. All right, here we go. Okay, and then let's see if you can see if I change this input, I can change the input all day, and nothing happens until I have a rising edge of the clock, and then on the rising edge of the clock, the output is going to change. Okay, so the input can change, doesn't matter, the input changes. Only when we have a rising edge of the clock is the output going to change. Okay, so that's the memory component of this thing. All right, so then we can add one more additional thingy in here, which is, let's see here, a multiplexer, right? So put a multiplexer in here. We'll put that multiplexer in between the input to the flop and the input to the register, right? And then we will loop our flop's output back around to the input there. Okay, cool. There we go. All right. And then, of course, we need to have a write enable input to select which flop input we're going to accept. Okay. So right now, the state of this register, this is a register. This is the simplest version of a register, right? We have an input to the register, data in. We call this as data in input. So I can label that here. Right, I'll call this data in. Okay, we have a write enable input, and then we have the actual state of the register. Sometimes this is called, I don't know what you call this. This is the value of the register, right? This is the current value the register has on it right now, okay? So let's take a look and see what's going on with this thing. So right now, the LED is on, which means that the state is a 1, okay? Okay, so the data in is a 1, right? So the data in is coming through here, right? And the write enable is a 1. Okay, so let's say we set the data, so when the write enable is a 1, that means that this multiplexer here is going to take whatever is on the data in input and it's going to pass it through to the multiplexer's output, which is going to get fed to the input of this D flip-flop. So if I change my data in input, you can see that the D input to the flop is changing, okay? But the actual state of the flop is not going to change until the next rising edge of our clock, okay? So the state of the flop is not going to change until the next rising edge of the clock, Okay, so right now what we have here is we have the data in, the data that we want to write to this register is a 0. Okay, the state of the flap though is currently a 1. Okay, and our write enable is set, right? So with this write enable is set to a 1, it's saying that basically we're passing our data input or our write input to our flap is going to become a 0. So the state of the flap will become, the state of the register is going to become a 0 on the next rising edge of the clock. So let's cause a rising edge of the clock to happen, and you can see that now all of a sudden the state has changed to reflect the data in of the register. Okay, so now we can do the same thing. What if we say we want the data in to now be a 1? Okay, now what you can see is that still this this D input, right, or the output of the multiplexer is following the data in input to the multiplexer because the write enable is a 1. Okay, so what if we want to disable writes? Okay, so we're going to make the write enable a 0. Right now, once the write enable is 0, now it doesn't really matter what the data in input is. The multiplexer is always going to select the 0 input from the multiplexer, which is just being fed back from the flip-flop's state, right, or the Q output of the flip-flop. Okay, so even though our data input is a 1, this register is not accepting new values at this point. Okay, so because the write enable is a 0, this multiplexer is not allowing anything new to be written to our flip-flop. So we can set the clock and toggle the clock all day, but the state of the flip-flop is not going to change because the write enable input is a 0. Okay, once write enable becomes a 1, then now all of a sudden this multiplexer is going to accept the new data to be written to the flop state, and when we toggle the clock, you can see that the new state has been written to the flip-flop. Okay, so this is sort of like the basics of how a register works. So let's actually take this register design that I've created here, and we're going to create a new circuit. We're going to call it a 1-bit register. Okay, here's my 1-bit register, and now I'm going to copy Control A and Control C, or Command A, Command C on a Mac. And I'm going to just paste that in. Whoops. Can I paste it? Oh, here we go. All right. I'm going to paste it in. Okay, so I'm going to call this thing. Looks like something bad happened here. Here we go. So my circuit is going to be called 1-bit register. Okay. Okay. So what I need to do here is I need to, in order to make this sub-circuit work, I need to modify this thing a little bit. I can't use an LED as an output. I need to use an actual bona fide output device here. And that output device, I will call it Q. Okay, my input device, I need to call that, I'll call it D in. All right, I'm going to get rid of this data in label here. I'll also get rid of this write enable label, and I'm going to call this one write enable. Okay, and then we should also have a clock input for this thing too. We won't use a button for the clock. We'll use a real clock input. Okay, here we go, and we'll label this input clock. Okay, so we've created this device. This is a sub-circuit, okay, which we can just basically place into our main design. All right, so if I go back to my main design, I'm going to delete everything here, and then I'm going to do circuits. I'm going to say insert sub-circuit, and I'm going to insert this 1-bit register. And you can see that when I insert this 1-bit register, it's just inserted as a block. Okay, and the stuff that's inside of this block, if I double click on it, I can see the stuff inside of this block is the stuff that I put inside of this 1-bit register thing. Okay, This is called hierarchical design. It's kind of used pretty widely in digital logic. Okay, so here's my 1-bit register. I think we've done this in previous classes. Okay, so now what we're going to do, okay, so now let's go back and let's actually start to build our adder that we put together, or I'm sorry, our computer that we put together on the blackboard or in the lecture. Okay, so what you can do is you can put your 4-bit adder. If you've built a 4-bit adder from your previous homework, you can place that in here. Mine, I built it, but I probably lost it somewhere. So what I'm going to do is I'm going to just cheat here, and I'm going to use the built-in ALU function. Okay, so this is an ALU. It's like an adder on steroids, right? It's got an adder, but it's also got a bunch of other functionality that you can add, that you can give to it here, right? So I'll just so what we're going to do is we're going to create. I'm going to force this ALU to have a bit width of 4. I'm going to give this input a bit width of 4, and I'll just kind of demonstrate what the ALU does before we move on too much here. Right, so basically we can have 2 4-bit inputs feeding into this ALU, and then our answer is going to be we'll make it an output here, which will be, well, actually, let's not make it an output. Let's make it a hex display so we can see the output value in hex. Okay, but let's see here. What's the problem? Oh, yeah, and then our opcode, we need to give it an operation to do. So this opcode, this is a 3-bit opcode, which is going to tell the ALU what to do. Okay, so if I give the ALU, say I wanted to add, let's see here, this is an AND operation, right? So we're ANDing the 2 numbers together, right? If I wanted to add the 2 numbers together, I give it an operation code of 0, 1, 0, and that's going to cause the ALU to calculate A plus B, basically, right? So this is called arithmetic and logic unit, right? So it does arithmetic like add and subtract, but it also does logic. So each one of these wires represents a 4-bit bus. So that's good, but the problem we have here is that our register is really only a 1-bit register, right? So what we need to do is we really want, we're good with this register. We just want it to be a 4-bit register, not a 1-bit register. So let's create a 4-bit register. Okay. And then inside of this 4-bit register, I'm basically going to just place a bunch of these 1-bit registers. Now, while I'm doing this, I just want to remind you guys that if you kind of look at the way that I route the wires um, in this design, you'll notice that I'm trying to keep everything kind of spaced out and orthogonal. Okay, a lot of people, I've seen a lot of students when they get into these digital designs, they'll just kind of route wires using the shortest path from one point to another without really worrying about trying to keep things spaced out. And what ends up happening a lot of times is that they get unintended wires crossing each other, and it just completely screws up the design and it won't simulate correctly inside a Circuitverse. And so, of course, you spend a lot of time going through a rat's nest of wires trying to find a problem like that. So, when you watch me route this stuff, keep that in the back of your mind, how I keep things spaced out and how I just try and keep the wires running, sort of like as orthogonally as possible. Okay, and there's sort of like an overall plan about how all this stuff is routed, as opposed to just kind of putting things in and sort of sorting out the details later. And that it's definitely worth spending a few minutes trying to acquaint yourself with the user interface in order to get comfortable enough to be able to route things cleanly so that you don't waste a ton of time after your design is finished and you know there's some kind of a problem that you can't find. So here is my right enable. That's a single bit that I'm going to feed the same right enable bit, the same right enable signal to all of my, to each one of my 1-bit registers here, right? And I'm going to do the same with the clock, right? The clock is a 1-bit signal, and I'm going to feed the same clock to all of the 1-bit registers, okay? The thing that's going to be different for all the registers is the data in. Okay, so my data in to my 4-bit register, I'm going to have 4 bits, of course, right? And what I want to do is that this is whatever comes out of this thing. This is going to be a 4-bit bus. So I'm going to take this 4-bit bus and I'm going to split it into 4 1-bit buses. Okay, so I have the first number you enter is the input bit width. The second number you enter is a space separated output bit widths, right? So I have 4 1s separated by spaces here. Okay, and so this is going to give me, so on this side here, this little dot is going to be a 4-bit bus, and whoops. Oh, that's weird. Okay. Anyway, so we have a 4-bit input bus that's going to get fed to 4 1-bit output buses. Let me clean this up a little bit here. Okay, so this is bit 0, right? And so that's going to get bit 0 is going to go to, this will be this will be my bit 0 1-bit register. Here's bit 1. Bit 1 is going to go to my register for bit 1 and so on. So each one of these bits from my 4-bit input bus is going to go to one of my bits from my 1-bit register, right? And then of course the 1-bit register is going to generate, each one of those 1-bit registers is going to generate an output. Okay, so I need to basically take this output from each one of these 1-bit registers. I need to like kind of coalesce them using one of these splitters again. So I'm going to have a 4-bit input. Okay, it's going to be that's going to be one side, and then the output is going to be 4 1-bit outputs. Actually, I think I did that wrong. I think I want it the other way around. I think I want 4 inputs and 1 out. Well, that's not right either. There we go. All right, I guess that's all I get. Need to change the orientation of this thing. Okay, so bit 0, this is my bit 0 register, is going to go to bit 0 of my splitter. Bit 1 goes to bit 1, and so on. Okay. And now, so these are the 4 individual 1-bit outputs, and those are going to get fed through the splitter to we'll make this a 4-bit output. So here's my 4-bit output. Okay, so I need to give these things names. I'll call this out. I will call this one that gets fed to the clock, I'm going to call that clock. The one that gets fed to the right enable, I'll call that right enable. And then this one is going to be called DN, data in. Okay, so now I have this 4-bit register here. Okay, so what I can do is I can basically place this 4-bit register in my top level design. All right. So here, so my D in to my register is going to come from the sum that's being generated by my adder. Okay. And then of course I'll have, so this is what I was calling when I was drawing it on the board. This is what I was calling the accumulator. So let me just put a label on this thing so everybody knows what I'm talking about. This 4-bit register that I've just generated here, this is the accumulator, and the value that it's spitting out, right? This is the state of the accumulator. This is the value that the accumulator holds. Okay. Okay. So what we want to do is we want to have let's have a write enable input. I will use, well, I'm not going to use, I'll have a write enable input, which will be, whoops, oh, what have I done here? Which I'll set to a 1. Okay, so we'll always enable writes on this thing. And we'll have a clock input, which I'm going to have, I'll use a push button for my clock input here. And that's going to be my clock. Okay, so what this thing is going to do is every time I toggle the clock, it's going to take the output of my adder. Let's just see what let me just create a new, create a new flip or a new hex display here, and we will tie this hex display to the output of the adder. Okay, so what you can see is the adder's output is 4. Okay, that's 1 plus 3, right? This is 1 in binary, and this is 3 in binary. And then this thing here, this is the command that tells this arithmetic logic unit to calculate the sum of the two inputs. Okay, so the sum, of course, of 1 plus 3 is 4, but that value, that sum, has not gotten locked into my 4-bit register yet. Okay, so in order for that to happen, I need to toggle my clock. And what you can see is on the rising edge of the clock, that new value 4 gets transferred from the D in to the D out. Okay, and as long as my write enable is a 1, then I'm going to be able to hold that value. Okay, so let's say I change the two inputs here, my A plus B. I'm going to change these two inputs to 1 plus 1 instead of 1 plus 3. So now the sum of 1 plus 1 is now 2. Okay, and if I toggle my clock to create a rising edge, that's going to cause the value 2 to get latched into my accumulator. Okay. All right, this is kind of what we talked about, right? But we haven't really written a program yet, right? It's just we're just kind of hard coding these two inputs, right? So we've hard coded these inputs 1 plus 1 together, right? And then we have this thing, this adder thing that can add them together and latch the results. Okay, which is fine. That's fine. But I want this thing to do a little bit more than that, right? I want it to be able to. It's not really programmable, right? I have to program this thing by actually changing or hard coding these inputs to the system, right? But I don't want to do that. What I want to do is I want to take the current value of the accumulator, which is being output here on this output, and I want to wrap that current value back around to the input of the adder. So let's do that real quick. So I'm going to change this guy here so that one of the inputs to the adder is going to be the current value of the accumulator. Okay, so what you can see now is I have the current value of my accumulator is 2, and that is going to get shoved back into my adder. And then I have another input to my adder here, which is 1. Okay, and you can see that when I toggle the clock, so basically what I'm doing is I'm adding 2 plus 1, I'm generating a sum of 3, and then when I toggle the clock, that value of 3 is going to get reflected in the output, and then of course 3 is going to then get wrapped back around to my adder. I'm going to add 1 to it to generate the sum of 4, and then if I toggle my clock again, then that value of 4 is going to get latched in my accumulator. Okay? Which this is, okay, so this is a little bit closer to what I wanted, right? So we have this accumulator that's remembering the value. It's kind of like a variable value, right? It's a value of a single variable. It's only a 4-bit variable, but that's okay, right? It's just for demonstration purposes. We could have made it longer if we wanted to. And that variable is just getting incremented by 1 every time, right? But it's still not really programmable because I have to kind of hard code the increment here, right? If I have to set the increment by sort of like messing with this hard-coded input thing over here, right? What I really want to do is I really want to be able to write a program, okay, that can add different numbers to my accumulator on every clock cycle, right? The way I've got this thing configured now is I'm always adding the same number to my accumulator, right? The accumulator's let's say we're always adding this hard-coded 1 value, right? So every time I toggle a clock, I always add 1 to it, right? Okay, it's kind of stupid, right? So I want to be able to change this thing here, this input value, with a program, okay? And the way I'm going to do that is I'm going to use a thing called a memory, all right? Okay, so let's get into that real quick. So we have a memory here somewhere. I think it's under, where is the memory? Here we go. Here's my memories here. I have 3 memories available to me. I have a ROM, a RAM, and an EEPROM, okay? So what I'm going to do here, though, is I'm just going to use the ROM. This is kind of like the easiest one to use, okay? So my ROM, basically it has, 2 inputs and 1 output, okay? So you can think about this ROM as kind of like an array, right? It's an array. It's a 16 element array. Okay, so this is a memory that only can remember 16 bytes, right? And each little square in this array represents 1 byte. Okay, so I can change this to, let's say, EF. Okay, this is the value EF hex. Okay, that's a 1 byte value that I can put into this ROM at address 0. This is index 0 in the array. So index 0 in my ROM or index 0 in my array has the value EF. Okay, here's index 1. That's the second element of the array. We call it index 1. Let's call it BB. We'll put BB in there. So now index 1 in my array has the value BB, right? And so on. Okay, so now every element in this memory or every element in this array now has a different value. Okay, so now what I can do here, I want you to ignore the circuit that I made over there. Oops, looks like my computer's about to die. Better plug it in. Okay, so ignore that circuit that I made over there for a second. And then what we're going to do is we're going to put a number on this address input. This is called the address input to my memory. So I'm going to have a hard-coded 4-bit input. Let me change this to a 4-bit input. And I'm going to then take the output and I'm going to figure out what's going on the output. So I'll use a hex display to show the output of this thing. Here we go. So here's my hex display. I have an 8-bit output of this memory. And what I've done is I've taken that 8-bit output and I've split it up into 2 4-bit buses here. Here's the first 4 bits. Oops, excuse me. I've reversed them. This is terrible. It's not what I wanted to do. I want to take the most significant 4 bits, bits 7 down to 4, and hook them up to this hex display here. And I want to take the least significant 4 bits and hook them up to this. So this is the, on the right side, this is usually the least significant part of the number, and the left side is the most significant part of the number. So what you can see here is I have given an address 0, 0, 0, 0. And the memory is now highlighting in dark green the cell of the memory that corresponds to the address that we've given it. And on the output, on the data output of our memory, we're seeing that the value that's stored at the address that we've given it. So in this case, 0, 0, 0, 0 corresponds to the first cell in memory here, first cell in this array, which has the value EF. We can see it because we can look at the array here. And you can see that the memory is now outputting the value EF onto its output data bus. Okay, let's say we wanted to look at a different address in memory. Let's say we want to look, instead of address 0, 0, 0, 0, we want to look at address 0, 0, 0, 1. Right, 0, 0, 0, 1, I've given it value BB. The data that lives at address 1 is BB. So I'm going to change my address to be 1. And now my memory has highlighted in dark green the cell that corresponds to address 0001. And you can see that the data that's being output is actually BB, which is the data value that lives at address 1. Right, and we can keep doing this, right? We can change it to address 2, which is 0010 in binary. That's this cell here, this green cell right here, which has the value 11 in it. And you can see that the data bus is pushing out the value 11. Okay, so I would encourage you to basically hook this up in Circuitverse. All right, this is a pretty instructive way of understanding memory. We're going to come back to this later on in the semester. Okay, I want you to see how this works. Okay, so now what we're going to do is we're going to hook this thing up. We're going to hook this memory up to our adder circuit that we built over here that includes our accumulator, okay? And we're basically going to build sort of like a very primitive computer. And so the way we're going to do this, we talked about when we were talking about the writing instructions for this computer, we said that each byte in our memory is going to be one instruction, right? And the first 4 bits, right, the high order 4 bits of the instruction are going to be this opcode, right? So we said that 400000 means we need to do an add, okay? And we didn't really define what any of the other combinations, the opcode combinations would be. And then we said that the low order 4 bits, these are going to be the thing that we're going to add to the accumulator, okay? So what we can do here is we can basically replace this number here. Right here we have hard-coded 1. We're gonna, in our circuit that we've generated, we have hard-coded the number 1 to be the thing that we're going to add to our accumulator. So every time, whatever the accumulator's value is, in this case its value is 7, we're going to add the value 1 to 7 to get 8. And then every single cycle, we continually add the same number to the accumulator. We always just add 1, okay? So instead of doing that, we're going to delete this, and we're going to take the output of our memory. Let me see if I can actually just move this memory over a little bit so they're all kind of closer together. Okay, so what I'm going to do now is just, I'm going to take the low order 4 bits of the output of my memory, and I'm going to hook those up to the input of my adder, okay? And so now what I'm going to do is I'm going to modify the contents of this memory, okay? So remember the high order 4 bits I said need to be 0, and the low order 4 bits need to be the number that I'm going to add to my accumulator. Here we go. Okay. All right, so you can see that I've modified this I've modified this thing so that all of the high order 4 bits are always 0 in all of the memory locations, and the low order 4 bits are some other number, and that number, in this case, my address that I'm sending out is 2, so I'm looking at this data byte 02 in memory, right? And this number 2 is the number that's going to get added to my accumulator. Okay, so my accumulator's current value is 0. I'm going to add 2 to the accumulator's value of 0, and the result is going to be 2, right? So if I hit the clock, then you can see that I have gotten the value 2 on the output, right? So if I change the address in memory, let's say I move to address 0. Okay, address 0 in my memory contains the value 0, 1. Okay, 0, 1 is telling us that it's an instruction basically for this computer, right? The first part 0 tells us that we're doing an add operation, right? We're not really using that in this computer. The second part 1 tells us how much we're going to add to our accumulator, right? So the 1 from our memory goes to our adder, right? And then we take the current value of the accumulator, and that also goes to the adder. So we take 1 from our memory plus 2 from our accumulator. The sum becomes 3. And if we hit the clock, then the accumulator value gets latched, right? Okay, so this is perfect. So now the very last thing that we want to do here is we want to basically be able to step through this program one instruction at a time. All right, so what you can think about here is you can think about this sequence of values that I placed in memory, 0, 1, 0, 1, 0, 2, 0, 0, 0, 4, 0, 6, right? This is a sequence of instructions, right? What it's telling the computer to do is the first instruction is telling the computer to add 1 to the current value of the accumulator. The second instruction is telling it to, again, do the same thing, add 1 to the current value of the accumulator. The third instruction is telling it to add 2 to the current value of the accumulator. Right? Then the fourth instruction is telling it to add 0 to the current value of the accumulator, and so on. Okay, so what I would do is I want to step through these instructions one at a time, basically, right? We want to start on the first instruction, address 0, and we just want to step through the instructions one at a time. Okay, so the input to this thing, right? We need an input that's going to get incremented on every clock cycle, right? So right now we're hard coding this input to 0, 0, 0, 0, right? But we don't want to do that. What we want to do is we want to have a register that stores the current instruction that we're working on, and every time we have a clock, we want to increment that instruction index to point to the next instruction. So I don't have to come here and manually update it every time I want to change the instruction that I'm executing. Okay, so here's how I'm going to do that. I'm going to take my 4-bit register. Here's my 4-bit register here. Okay, so this 4-bit register, I'm going to replace the instruction index there that I had, the address, with my 4-bit register. Okay, and I'm going to let's see here. No, I'm not going to hard code. I'm going to hard code write enable to a 1 because it's going to get written on every clock cycle. Okay, so I'm going to change this to a 1 somehow. How do I do this? No. There we go. Because you have to double click on it. Okay. All right, so then we're going to change this to a 1, and then our clock, here's my clock. This is going to be the clock. It's the same clock for both of my registers. Oops, not DN, clock. There we go. All right, and then on every time the clock cycles, every time we get a rising edge, of a clock. We want to update the value in our, update the value in this register. So what we're going to do now is we're going to take the current value here, and let's see here, this needs to be a 4-bit ALU. We're going to add 1 to it. Operation I'm doing on this is going to be 0, 1, 0, right? 0, 1, 0 tells us to add. Okay, so I'm going to take the current value, I'm going to add 1 to it, and that is going to give me the new value. Okay, so if I just increment the clock, what you're going to do, I'm going to push this button in a second to increment the clock. So watch the address here, right? Watch what address is getting pointed to. And every time I increment the clock, I'm going to take my current address, which is right now 1, 0, 0, 1. I'm going to add 1 to it. Or I'm sorry, 0, 1, 0. It's 2. 0, 1, 2. This is 2. I'm going to increment it by 1, and I'm going to put the result back in the DN. Okay. Let's put a 7 or a hex display here, so we can see what address we're at. So this is the address right now. Let me put some text down here. This is the address. This is the address of the instruction that's currently being executed right now, right? We're at address 2. Address 2 contains the number 2, right? So we're going to take the number 2, we're going to add it to the current value of the accumulator, which is 6. The result of that will be 8. And then when we push the clock again, the new value 8 is going to get updated here. Okay? All right. And now we're at address 3, right? So we're at address 3 in our program, or instruction index 3. This is the third instruction. It's telling this third instruction is 0, 0. This is telling us to add the number 0 to our accumulator, right? So our accumulator's value is 8. We are going to take the value 8 and we're going to add that to 0. The sum, of course, is 8. 8 plus 0 is 8. And then once we push the accumulator, or once we push the clock, that new value of 8 is going to get latched into the accumulator. Okay. The next instruction here is 4, 0, 4. That's telling us to add the value 4 to our accumulator. So 8 plus 4 is 12, right? 12 in hexadecimal is C, right? So here our result is C. So as soon as I push the clock button, the value C is going to get latched into our accumulator, okay? And so on and so forth, right? So I'll do a couple more here. So now we're at instruction 5, right? So instruction 5 is right here in our memory, 0, 6, right? This is the number that's going to get added. So 0, 6 is telling us to add the value 6 to our accumulator, which is already C. So we have a C in our accumulator. If we add 6 plus C, let's see here, 6 plus 12 is 18, right? So, but 18 in hexadecimal is represented as 1, 2, right? And so you can see that we're going to throw the top the 1 away, basically, and we're just going to keep the 2, and so that's where this comes from. So we push the clock, we're going to advance to the next instruction and latch the 2. Okay, so now we have 2 in the accumulator, right? And now we're at address 6, or instruction 6, right? So instruction 6 is telling us to add the value C, which is 12, to our accumulator, right? So C, or 12 plus 2 is 14. 14 in hexadecimal is E, right? So we press the accumulator, and we then add that together, and now we latch E, right? We'll do one last one here. So we're at instruction number 7, right? Instruction 7 in our memory tells us to add 1 to the accumulator, right? So the current value of the accumulator is E. E plus 1 is F, okay, which is 15. And so then if you press the clock button, then we latch the F. Okay. So this is basically this is the beginnings of a simple computer. Okay. So what you can see we have here is we have a memory here. This is a memory that contains all of the instructions, right? So this computer really only has one instruction. It's an add instruction. It just tells us to add a 4-bit number to the accumulator. Okay, we could define other instructions, of course, if we wanted to. Maybe I'll make some videos about how to do that. But basically, it's a very simple computer, but we can write this, and so the sequence of these instructions that we program into this memory, this is called the program, right? So if I change the if I change the numbers that I write into this memory, I'm going to change the behavior of the program. I'm going to change the values that get stored in this accumulator. Okay, so basically these instructions that are in this memory right now, these are machine instructions. Okay, this is, obviously your laptop has a little bit more complicated set of instructions that it can recognize. Okay, of course, this only has one instruction. Your laptop has hundreds of instructions that it recognizes. But basically it's the same idea, right? So we have these machine instructions, they're encoded in binary, right? We've encoded these machine instructions in binary, and they are just simply executed by the computer in hardware. Okay, so the next part of the class, we're basically going to be learning about how can we write machine instructions. You don't have to write machine instructions in binary or in hexadecimal form, right? Nobody really does that. What you do is you actually write your program in a text file, and then that text file gets converted by another piece of software called the assembler into this format here that actually gets executed by the computer. But we're going to be learning about how to write these assembly instructions in order to make the computer do what we want it to do.